NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math problem-solving video. Today, we'll be solving a problem about a farmer's square land and calculating its perimeter. Let's start with the problem. A farmer has a square piece of land. For planting and working on this land, he uses 50 grams of seeds per square meter. If the farmer used a total of 5 kilograms of seeds for planting the entire land, what is the perimeter of his land? To solve this problem, we first need to determine the area of the land. We know the seed usage rate is 50 grams per square meter, and the total amount used is 5 kilograms. Let's first set up a relationship to find the area. Before we proceed, let's convert 5 kilograms to grams for consistency. 5 kilograms equals 5 times 1,000 grams, which is 5,000 grams. Now, we can set up a proportion. If 50 grams is used for 1 square meter, then 5,000 grams is used for x square meters. This gives us the equation x over 1 equals 5,000 over 50. Let's solve for x, which represents the area of the land in square meters. X equals 5,000 divided by 50, which gives us 100 square meters. Since we know the land is a square, we can find the side length. For a square, the area equals the side length squared. If we call the side length s, we have s squared equals 100 square meters. To find the side length, we need to take the square root of the area. The square root of 100 is 10, so the side length is 10 meters. Now, we can calculate the perimeter of the square land. The perimeter equals 4 times the side length. So that's 4 times 10 meters, which gives us 40 meters. Therefore, the perimeter of the farmer's square land is 40 meters. Let's summarize what we've learned in solving this problem. First, we established the relationship between the area and the amount of seeds used. Then, we converted units to ensure consistency in our calculations. We set up a proportion to find the area of the land, which was 100 square meters. Since the land is square, we determined that the side length is 10 meters. Finally, we calculated the perimeter as 40 meters by multiplying the side length by 4. This problem demonstrates how to use proportions and geometric formulas to solve real-world problems. Remember, for a square, the area equals side length squared, and the perimeter equals 4 times the side length. Let's look at our first example. If the area of a piece of land is 196 square meters, what is its length? To solve this, we'll use the formula that area equals length squared, and rearrange it to find length equals the square root of area. So, length equals the square root of 196 square meters, which is 14 meters times 14 meters. Therefore, the length of the land is 14 meters. Let's look at our second example. If the area of a piece of land is 256 square meters, what is its length? Using the same approach, length equals the square root of 256 square meters, which is 16 meters times 16 meters. Therefore, the length of the land is 16 meters. Now, let's try a more challenging example. If the area of a piece of land is 300 square meters, between which two consecutive integers does the length of this land lie? This is a bit different, because 300 is not a perfect square. We need to find the square root of 300 and determine which two consecutive integers it lies between. Let's calculate. 17 squared equals 289 square meters, and 18 squared equals 324 square meters. Since 289 is less than 300 and 324 is greater than 300, we know that the square root of 300 must be between 17 and 18. Therefore, the length of this land is between 17 meters and 18 meters. Let's look at one more example. If the area of a piece of land is 50 square meters, estimate the length with 1 decimal place. Again, 50 is not a perfect square, so we need to find which squares it lies between. We find that 7 squared is 49 square meters, and 8 squared is 64 square meters. So the length is between 7 and 8 meters. To estimate with 1 decimal place, let's try 7.1. 7.1 squared equals 7.1 times 7.1, which is 50.41 square meters. This is very close to our target of 50 square meters. Therefore, we can estimate the length as 7.1 meters. Today, we're going to solve a problem about finding the side length of a cube when we know its volume. Here's our problem. The volume of a cubic tank is 25 cubic meters. We need to find the length of each side of the cube. Let's make a guess, and then check it. Let's approach this problem systematically by creating a table that shows the relationship between a cube's side length and its volume. Remember, the formula for the volume of a cube is the side length cubed, or S cubed, where S is the side length of the cube. Now, let's create a table to see how the volume changes as the side length increases. This will help us find which side length gives us a volume of 25 cubic meters. Looking at our table, we can see that when the side length is 3, the volume is 27 cubic meters, and when the side length is 2, the volume is 8 cubic meters. Since our target volume is 25 cubic meters, the side length must be between 2 and 3 meters. Let's use a mathematical approach to find the exact value. To find a more precise value, we need to calculate the cube root of 25. Let's try some decimal values to get closer. Let's try 2.8. If we cube 2.8, we get 2.8 cubed, which equals 21.952. That's less than 25, so we need a slightly larger number. Let's try 2.9. If we cube 2.9, we get 2.9 cubed, which equals 24.389. That's still less than 25, but much closer. We can determine that the cube root of 25 is approximately 2.924 meters. It's important to understand that the cube root of 25 is an irrational number. This means that its decimal representation never terminates or repeats. With a calculator, we can get approximations, but the exact value is expressed as the cube root of 25. In real-world applications, we often use approximate values like 2.92, 2.924, or 2.9, depending on the level of precision needed. On a number line, we can visualize where the cube root of 25 falls. It's between 2.9 and 3, closer to 2.9. In conclusion, to find the side length of a cube with a volume of 25 cubic meters, we need to calculate the cube root of 25. The side length of the cube is exactly the cube root of 25, which is approximately 2.924 meters. This is a good example of how we can use the relationship between a cube's volume and its side length to solve practical problems. Remember these key points. First, the volume of a cube equals side length cubed. Second, to find the side length from the volume, you take the cube root of the volume. And third, when working with cube roots, sometimes the exact value is irrational, so we use approximations in practical applications. Welcome to our math lesson today. We're going to learn about square roots and perfect squares. This is a fundamental concept in mathematics that will help you understand more advanced topics later. Let's start by understanding what a perfect square is. A perfect square is a number that results from multiplying an integer by itself. For example, let's consider the number 4. If we multiply 4 by itself, we get 16. So 16 is a perfect square, and we can write this as 4 squared equals 16. To visualize this concept, let's draw a square with sides of length 4 units. Inside this square, we have a total of 16 small unit squares. This is why we call it a perfect square, because the number represents the area of a square with integer side length. Let's look at a few more examples of perfect squares. When we square 5, we get 5 times 5, which equals 25. When we square 6, we get 6 times 6, which equals 36. We can organize these perfect squares in a table to see the pattern more clearly. Here we have the number, and next to it, it's square. As you can see, 4 squared is 16, 5 squared is 25, and 6 squared is 36. Now, let's understand what a square root is. The square root of a number is the value which, when multiplied by itself, gives the original number. For example, the square root of 16 is 4, because 4 times 4 equals 16. We write this using the square root symbol as shown here. Let's look at some more examples of square roots. The square root of 25 is 5, because 5 squared equals 25. The square root of 36 is 6, because 6 squared equals 36. We can also find square roots of fractions. For example, the square root of 1 over 64 is 1 over 8, because 1 over 8 squared equals 1 over 64. Let's try a little challenge. Can you find the square root of 81? Take a moment to think about it. The square root of 81 is 9, because 9 squared equals 81. Let's visualize the square root concept geometrically. if we have a square with an area of 16 square units, then the length of each side is the square root of 16, which is 4 units. This shows the connection between the square root and the side length of a square with a given area. Let's summarize what we've learned about square roots and perfect squares. A perfect square is a number that results from multiplying an integer by itself. The square root of a number is the value that, when multiplied by itself, gives the original number. Geometrically, if a square has an area of a, then each side has a length of the square root of a. Let's recap our examples. The square root of 16 is 4, because 4 squared is 16. The square root of 25 is 5, because 5 squared is 25. The square root of 36 is 6, because 6 squared is 36. The square root of 81 is 9, because 9 squared is 81. Understanding square roots is essential for many areas of mathematics, including geometry, algebra, and calculus. Welcome to our video on cube roots of numbers. In this lesson, we'll learn what a cube root is and how to find cube roots of different numbers. If we understand what a cube is, then finding its roots becomes easier. A cube of a number is obtained when we multiply that number by itself 3 times. Let's consider a number like 3. If we multiply 3 by itself 3 times, we get 3 times 3 times 3, which equals 27. As you can see, 3 times 3 times 3 equals 27. We can also write this as 3 cubed equals 27. Let's look at cubes of some other numbers from 2 to 4. 2 cubed equals 2 times 2 times 2, which is 8. 3 cubed equals 3 times 3 times 3, which is 27. 4 cubed equals 4 times 4 times 4, which is 64. Let's organize this information in a table. We have the number in the left column and its cube in the right column. 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. Now, the cube root of a number is the reverse operation. If number 8 is a cube of 2, then we say that 2 is the cube root of 8. We write this as cube root of 8 equals 2. Therefore, number 8 is a cube, and its cube root is 2. We can express this relationship in 2 equivalent ways. 8 equals 2 cubed, and cube root of 8 equals 2. Here are some examples based on our table. The number 8 is a cube, so its cube root is 2. The number 27 is a cube, so its cube root is 3. The number 64 is a cube, so its cube root is 4. Welcome to our video on nth roots. In this video, we'll explore what nth roots are, how to work with them, and some important properties to keep in mind. Let's start with the definition of nth roots. Suppose x is a real number and n is a natural number greater than 1. The nth root of x, which we write as the radical symbol with x inside and n as the index, or as x raised to the power of 1 over n, is a real number y such that y raised to the power n equals x. This is the key relationship of nth roots. If y is the nth root of x, then y to the nth power equals x. This means we can express this relationship in 2 equivalent ways. X equals y to the power n if and only if the nth root of x equals y. In the expression for nth root, the value n is called the index or degree of the root. This is why we can say that in an nth root expression, n is called the index. Let's look at some examples to understand this concept better. First example, 9 equals 3 squared, so we can say that the square root of 9 equals 3. Second example, 1 over 10,000 equals the fraction 1 over 10 raised to the power 4. So we can say that the fourth root of 1 over 10,000 equals 1 over 10. Third example, negative 64 equals negative 4 cubed. So we can say that the cube root of negative 64 equals negative 4. Now, let's discuss an important consideration when working with nth roots. We need to pay attention to whether the index is even or odd. For even roots, like square roots or fourth roots, if x is negative, the root doesn't exist in the real number system. For example, the square root of negative 4 doesn't have a real value. For odd roots, like cube roots or fifth roots, the roots of negative numbers do exist in the real number system, and they are negative. For example, the cube root of negative 8 is negative 2, because negative 2 cubed is negative 8. Welcome to our math video. Today, we're going to learn about an important rule in radical expressions. What happens when we have an even root of a negative number? Let's start by defining our rule. if n is even and x is negative, then the expression y equals the nth root of x is not defined in the real number system. In other words, we can't have a negative number under an even root and get a real number result. Let's look at this more formally with our expression y equals the nth root of x. If we have an even value for n like 2, 4, or 6 and x is negative, there's no real number solution. This is because even roots of negative numbers result in complex numbers, which are outside the domain of real numbers. Let's look at some examples. Our first example is the square root of -4. Since the index is 2, which is even, and the radicand is -4, which is negative, this expression is undefined in the real number system. Let's look at another example. Our second example is the fourth root of -81. Here, the index is 4, which is even, and the radicand is -81, which is negative. So this expression is also undefined in the real number system. Let's look at one more example. This time, it's the 20th root of -5 to the power of 20. Again, the index is 20, which is even, and the radicand is negative. So this expression is undefined in the real number system as well. Let's examine 4 example problems. Each problem involves a radical expression, and we need to determine if it's meaningful in the real number system. Our first radical expression is the 101st root of -2 raised to the power of 100. To determine if this is defined in real numbers, we need to understand a key rule. When we have an even root of a negative number, the result is not a real number. However, when we have an odd root of a negative number, the result is a real number. Let's analyze our expression. We have the 101st root, which is an odd root of -2 raised to the power of 100. When we simplify, this equals negative the 101st root of 2 raised to the power of 100. Since we have an odd root, this expression is defined in the real numbers. It belongs to the set R, which represents all real numbers. Our second example is the 100th root of -2 raised to the power of 101. Let's recall our rule about radicals. Even roots of negative numbers are not defined in real numbers, while odd roots of negative numbers are defined in real numbers. For this expression, we have the 100th root, which is an even root of -2 raised to the power of 101. When we simplify, this equals the 100th root of -2 times 2 raised to the power of 100. Since -2 times 2 to the power of 100 is negative, and we're taking an even root, this expression is not defined in the real number system. Therefore, this expression does not belong to the set R of real numbers. We denote this by writing not an element of R. Our third example is the 2nth root of -2 raised to the power of 2n. In this case, the exponent 2n and the root index 2n are the same. This means we can simplify this expression directly. Let's use another important rule for radicals. When the exponent and the root index are the same, we can simplify the expression to just the base raised to the power of 1, which is simply the base itself. So, the 2nth root of -2 raised to the power of 2n equals the absolute value of -2, which is simply 2. Since 2 is a real number, this expression is defined in the real number system. Therefore, it belongs to the set R of real numbers. Our fourth and final example is the fourth root of -x squared plus 1. Let's remember our rule. Even roots of negative numbers are not defined in real numbers. For this expression, we have the fourth root, which is an even root. We need to determine if -x squared plus 1 can ever be negative. We know that x squared is always non-negative for any real value of x. So -x squared is always non-positive. Therefore, this expression does not belong to the set R of real numbers. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.